so much. I can't believe no one competes. I fall to my knees. So right now, I want to see desperate with a feeling. Lost in your eyes, think I stayed for a while. So I always want you to know that when I hold you, just know I mean to. And if you're falling, I'm falling with you. Don't want you doubting all the ways I want you. So if you need more, I'll give it to you.
All right. So, getting started a little bit later than I ideally would like to, but I had to shovel some snow this morning. And my neighbor, she's 100. She's turning 101 soon. And her sidewalk and driveway were covered in snow this morning, so I went out there and did hers as well. So that delayed me a little bit. And then I did some work on the stream. I got my Discord set up. I got all the links, like on all the channels and stuff, so that when people visit, they can find me on other platforms and stuff. And I did a couple other things, but yeah, Discord was the main thing. So that's set up now, which would be cool to have for people who drop in and want to like have a more persistent chat going on than the fragmented stream chat. Cool. So this morning we are starting on chapter 45, System V IPC. I am super psyched for this. System V IPC is apparently the original IPC system that was developed. The APIs aren't very file descriptor like. They have persistence in the kernel. So I'm guessing the POSIX stuff is going to be more my style or my preference. But it is great to have full context on the history of how IPC was developed within Unix in general and specifically in Linux. And then after this is a bunch of memory mapping stuff. So yeah, today I think I'm just going to try to get all the System V stuff done, which includes, if we check our index over here, let's see, the intro, message queues, semaphores, shared memory. Cool. So let's get started. Chapter 45. And I think if I bring up a terminal here, I think say T7 done, because we're done with chapter 47. That puts us over 2/3 done. And if I do get status, get LGA 1, 2. Oops, jump over to the Linux programming interface. And we say get status, get LGA. So yeah, okay, we're all up to date on our Git stuff. Cool. We get some matcha here. All right. System V IPC is the label used to refer to 3 different mechanisms for inter-process communication. Those mechanisms are message queues, semaphores, and shared memory. There are ways of doing those that are not System V related, but I think these are the originals. Message queues can be used to pass messages between processes. So I experimented with benchmarking message queues, I think yesterday. Yeah, yesterday. And basically, message queues have a limited message size that's really small, like 8K. And also, like, their bandwidth kind of sucks. You can't really pump a lot of data through them. So they're not really good for bandwidth, and they're not good for message size. So they're more for smaller messages that you're exchanging with other processes. Message queues are somewhat like pipes. Pipes actually performed way better than message queues on bandwidth. The problem with pipes is that you have to invent your own framing, your own message framing. And the atomicity of the messages with pipes, you have to make sure you're within the maximum pipe size. And if you're too big, if your message is too big, I think it's like might even be the same 8K setting as message queues. But if your message is too big, it basically means that you're not guaranteed atomicity in your writes. So bytes from your message, you can have message fragmentation basically. And so if you have message fragmentation in a streaming protocol where you're doing your own framing on that protocol, then things just kind of go crazy. So there is some just like concrete complications in doing messaging over named pipes or pipes in general, and especially when you have multiple concurrent writers. So yeah, I imagine the message queues have the big advantage in that you don't have to worry about atomicity, you don't have to worry about framing your messages, so you don't have to do like a length prefix, you don't have to do a delimiter, you don't have to have like a fixed message size, you don't have to have any type of like open close delimiting type system. So yeah, let's continue reading on. So the message queues somewhat like a pipes with different two important respects. First, message boundaries are preserved so that readers and writers communicate in units of messages rather than via undelimited byte stream. Second, such messages include an integer type field, and it's possible to select messages by type rather than reading them in order in which they are written. Okay. I think that's kind of like a priority, the type. I think I remember reading about that before. One other thing I wanted to just talk about here is datagram sockets, Unix sockets. Datagram sockets, I feel like, give you a lot of the same benefits of message queues and have much higher performance when it comes to bandwidth. I think the downside with datagram sockets is they might not be reliable, in that if your buffer fills, I think the kernel might just throw your message on the ground, just not even handle it. That might be just for UDP datagram, because it's in the name unreliable datagram protocol. The unreliable part means that the kernel can just throw away your message if it wants to. But I don't know if that applies to datagram protocols on Unix domain sockets. So I would have to learn more about sockets, which we will in later chapters. But so far, I feel like datagram protocols, socket API is the way to go for doing message sending instead of using these message queues. Semaphores permit multiple processes to synchronize. I guess to go back to the type field before we move on, the type field allows you to select by type, which is interesting. It's kind of like a subscription, if you're familiar with PubSub, where you have a subscription prefix. In this case, it's just an integer, and you say, I'm interested in a message of these types. And I wonder if you have multiple readers, it's not going to be a PubSub. It'll be a fan out, basically. I think that's the way message queues work. All right, let's move on to semaphores. Semaphores permit multiple processes to synchronize their actions. A semaphore is a kernel maintained integer value that is visible to all processes that have the necessary permissions. A process indicates that to its peers that it's performing some action by making an appropriate modification to the value of the semaphore. Shared memory enables multiple processes to share the same region, called a segment of memory, i.e. the same page frames are mapped into the virtual memory of multiple processes. Since access to user space memory is a fast operation, shared memory is one of the quickest methods of IPC. Once one process has updated the shared memory, the change is immediately visible to other processes sharing the same segment. Although these three IPC mechanisms are quite diverse in function, there are good reasons for discussing them together. One reason is that they were developed together. First appearing in the mid-1970s, a long time ago, in Columbus Unix. Columbus Unix, I never heard of that. This was a Bell internal Unix implementation used for database and transaction processing systems for telephone companies, record keeping, and administration. Around 1983, these IPC mechanisms made their way into mainstream Unix, and by appearing in System V, hence the appellation System V IPC. A more significant reason for discussing the System V IPC mechanisms together is that their programming interfaces share a number of common characteristics, so that many of the same concepts apply to all these mechanisms. Because System V IPC is required by SSV3 for XSI conformance, it is sometimes alternatively labeled XSI IPC. This chapter provides an overview of the System V IPC mechanisms and details those features that are common to all three mechanisms. The three mechanisms are then discussed individually in the following chapters. System V IPC is a kernel option that is configured via the config sysv IPC option. To be honest, I've never ran into a program that uses System V IPC that I'm aware of, I should say. I'm sure I've used programs that use it, but first, I'd just like to ask the AI what syscalls are used by the sysv IPC functionality in Linux. One multiplex syscall plus a couple of helpers. Single syscall IPC. Man2 IPC. So it is its own little syscall. It's a common kernel entry point for the System V IPC calls for messages, semaphores, and shared memory. Call determines which IPC function to invoke. The other arguments are passed through the appropriate call. So you say, hey, this is the thing that I want to call. And then first, second, third, and a void pointer. And a long fifth. So a bunch of different arguments. User space programs should call the appropriate functions by their names. Only standard library implementations and kernel hackers need to know about IPC. I mean, need to know, but want to know. I am in the want to know camp. Or maybe I'm just a kernel hacker. No, I'm not a kernel hacker. I feel like you have to be patching the kernel to be called a kernel hacker. On some architectures, for example, blah, 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 I don't care about this. So message GTL, message get. So all the message, the semaphore prefix, the shared memory, SHM prefix, and then there's a sysv IPC document in the user manual. But it seems like all the, oh, these syscalls, message GTL? I don't think that's a man2. Let's look it up, man syscalls, and just search for that. See, there are other syscalls. Let's see. If we just man up message CTL goes to the 3P, which there's also 2. Yeah, on newer architectures, Linux has split the multiplexer into real syscalls. So if we do man syscalls and I search for IPC, so there's an IPC and then there's always individual shared memory, message, and semaphore. Huh. These are just signals that it gets. Huh. Well, at least Bash doesn't use it. At least from what I can tell. Okay. So if you man up syscalls and look for a shared memory, these are the system v IPC shared memory syscalls. If I man up shm open, that's a libc. Okay. Basically, there's a single IPC entry point into the kernel, like a single syscall called IPC. And then later on, Linux introduced all of these other individual syscalls that are separate. And my only guess, they said they did it for like cleanliness or some bullshit. Clean syscall is like, what is clean? I hate it when people use the term clean in software. It's so subjective, but like some people might say, oh, having a single IPC syscall would be cleaner than having a bunch of different ones. It's certainly more conservative when it comes to like conserving syscall numbers and limiting the API surface. So I hate this word clean, but my guess is that they did it to make it easier to invoke individual things instead of having to go through this IPC thing and pass in like weird, like if I do the man2 on IPC, like this signature is insane, you know? And you have to call it using the syscall, whereas if I do man2 on like message get, like it's a very natural API. You got a key, you got an integer message flag, and it returns an integer. It's like much more friendly than this nonsense. My guess is that they did it to make it a little bit more easier to invoke. You're not multiplexing a bunch of stuff onto a single syscall. Maybe even like make static analysis tools easier, because instead of everything going through the same IPC thing and then you have to like code out the parsing of the arguments and everything, it's like, okay, I can just look for a message get, and if message get is there, then I know that I'm getting a message. I don't have to like do extra work. And like if you're writing an assembly program, like assembly, you're literally just copying an integer into like RAX or whatever. So it's like, it would be nice if like you had different integer numbers for the different actions that you're taking. I don't know. I don't have enough of a intuition as to why they did it, and I don't like AI's reasoning here, but it is good to know like all of the system v IPC functionality maps onto either one syscall called IPC or a set of syscalls that are available on modern Linux kernels that map to the different functions that are provided. Okay, let's continue on. API overview. Table 445.1 summarizes the header files and system calls used for working with system v IPC objects. Let me finish off my matcha here. Oh. Okay. Some implementations require the inclusion of sys types before including the header files shown in table 45.1. Some older Unix implementations may also require the inclusion of sysipc.h. No version of the single Unix specification requires these headers files. On most hardware architectures on which Linux is implemented, a single system call IPC acts as the entry point to the kernel for the system v IPC operations, and all the calls listed in table 45.1 are actually implemented as library functions layered on top of the system call. Two exceptions to this arrangement are alpha and IA64, where the functions listed in the table really are implemented as individual system calls. This somewhat unusual approach is an artifact of the initial implementation of system v IPC as a loadable kernel module, although the actual library functions on most Linux architectures throughout this chapter will refer to functions in table 45.1 as system calls. Only implementers of C libraries need to use the IPC syscall. Any other use in applications is not portable. Summary of programming interfaces for system v IPC objects. So you got a header file, sys message, sys semaphore, sys shared memory. I didn't realize sys is for sysv. Maybe it is, maybe it isn't. Data structures are message queue, semaphore, shared memory. Create open is message get, semaphore get, shared memory get plus shared memory at. Close object, there's no concept of closing, except for shared memory, which is shared memory DT. Control operations, message CTL, semaphore CTL, shared memory CTL. performing IPC, message send, message receive, semaphore op, test, adjust semaphore, and then just accessing memory is how you do the shared memory. IPC operations. Creating and opening a system via IPC object. Each system via IPC mechanism has an associated get system call, which is message get, semaphore get, or shared memory get, which is analogous to the open system call used for files. Given an integer key analogous to a file name, the get call either creates a new IPC object with the given key and returns a unique identifier for that object. Or returns an identifier of an existing IPC object with the given key. We'll loosely term the second use of opening an existing IPC object. In this case, all that the get call is doing, so it's an upsert basically, or not an upsert. It's like a create or get. It's like an open with an ocreate. Ocreate. In this case, all that the get call is doing is converting one number, the key, into another number, the identifier. In the context of system via IPC, the object doesn't carry any of the connotations associated with object-oriented programming. The term merely serves to distinguish the system via IPC mechanism from files, although there are several analogies between system via IPC objects and the use of IPC objects differs in several important respects from the standard Unix file I/O model, and this is a source of some complications when it comes to when using the system via IPC mechanism. Yeah, I mean it's not compatible with like select and epoll and stuff like that. An IPC identifier is analogous to a file descriptor in that it is used in all subsequent system calls to refer to the IPC object. There is, however, an important semantic difference. Whereas a file descriptor is a process attribute, an IPC identifier is a property of the object itself and is visible system-wide. All processes accessing the same object use the same identifier. This means that if we know an IPC object already exists, we can skip the get call, provided we have some other means of knowing the identifier of the object. For example, the process that created the object might write the identifier to a file that can then be read by other processes. The following example shows how to create a system v message queue. So we say message get, and then we give it a key, and then we say, hey, IPC create, IPC, and then these are the bit mask or the permission bits. So we say the user should be able to read, the user should be able to write. And then if I go back and say ripgrep for message get, I should get chapter 43 where I experimented with the benchmarking of system VIP message queues. And you can see here, down here, this is what we do. We say, hey, it's going to be pretty much what I said there. Just different syntax. An IPC private is just a private key. So it's basically 0. So that probably means a key that only can be used within the same process. As with all of the get calls, the key is the first argument and the identifier is returned as a function result. We specify the permissions to be placed on the new object as part of the final. So that's the other thing. Is like these aren't being stored on the file system, but they still have permission bits similar to files on the file system, which is a bit confusing. And they should honestly just have like, I think if I go under CD chapter 43 here, and I do my build, no, it's not make. Build, measure, sysv, and I do like 1010, and then I ls under dev system Message. Let's ask AI here. If I create a sysv IPC message queue, does Linux put it anywhere on the file system, even if it is virtual? No. So there is no file system representation for it. I think some of these things like postage message queues, if I do build measure POSIX message queues, I do like, oops, 1010. Now under dev message POSIX, grep msg, kmsg, q, mq, ls dash la under dev mq, ls dash, we'll do like a find under dev for type directory, and there's mq, shared memory, wow, I have 32 cores on this thing. Sure it's not under here. Let's go back here, say, what about POSIX message queues? Yeah, devmq. So if I run this thing again, I'll do like, and if I do this again, I give it like another 0 here, and then I do this, you can see it shows up here. Or if I kill it, it'll stick around, I think. Yep. So yeah, POSIX message queues are written to the disk. That's what I was trying to, or they're not. There's a file system representation, even if it's just virtual, whereas systemv, it's just stored in the kernel, and good luck finding it. We specify permissions to be placed on a new object as part of the final flags argument to the get call using the same bitmask constants as are used for files. In the above example, permission is granted to just the owner of the object to read write messages on the queue. The process mask is not applied to the permissions placed on the newly created IPC object. Oh, umask is not applied, okay. Several Unix implementations define the following bitmask constants for IPC permissions. So-and-so. These correspond to so-and-so. To get corresponding groups and permissions bitmask, these constants can be shifted 3 bits, 3 and 6 bits. These constants are not specified by susv3, which employs the same bitmasks as are used for files and are not defined in glibc headers. Each process that wants to access the same IPC object performs a get call specifying the same key in order to obtain the same identifier for that object. We consider how to choose a key from the application for an application section 45.2. Oops, sorry. I got kicked over to the wrong page here. We are at, how did I get all the way over here? Wow, something happened weird there. 924. Oops. That's 924. All right, IPC keys. System V IPC keys are integer values represented using the data type key underscore t. The IPC get calls translate the key into a corresponding integer IPC identifier. These calls guarantee that if we create a new IPC object, then that object will have a unique identifier, and that if we specify the key of an existing object, then we'll always obtain the same identifier for that object. Internally, the kernel maintains data structures mapping keys to identifiers for each IPC mechanism, as described in section 44.5. So how do we provide a unique key? One that guarantees that we won't accidentally obtain the identifier of an existing IPC object used by some other application. There are three possibilities. Randomly choose some integer value, which is typically placed in a header file included by all programs using the IPC object. The difficulty with this approach is that we may accidentally choose a value used by another application. Specify the IPC private constant, is what I did, or that's what I did in the code that the AI gave me, as the key value to the get call when creating the IPC object, which always results in the creation of a new IPC object that is guaranteed to have a unique identifier. Employ the ftalk function to generate a likely unique key. Using either IPC private or ftalk is the usual technique. Generating a unique identifier with IPC private. When creating a new IPC object, the key may be specified as IPC private as follows. In this case, it's not necessary to specify the IPC create or IPC exec-l flags. This technique is, my flag is not necessary here. Foreground, no, vim, measure, sysv, IPC. Yeah, so here, I did specify that, right? Yeah, down here. I did IPC create, which is not necessary. And I blame the AI for that. Make, build, measure, sysv, IPC, 1000, 1000. Yeah. This technique is especially useful in multi-process applications where the parent process creates the IPC object prior to performing a fork, with the result that the child inherits the identifier for the IPC object. We can also use this technique in client-server applications, i.e. those involving unrelated processes, but the clients must have a means of attaining the identifiers of the IPC objects created by the server, and vice versa. For example, after creating an IPC object, the server could then write its identifier to a file that can then be read by clients. Interesting. Generate a unique key with ftalk. The ftalk file to key function returns a key value suitable for use in a subsequent call to one of the system v IPC get calls. So you give it a path name. Seems like they wanted the benefits of like the file system, but they didn't want to bother with all the work and integrating with it in edge cases that involves. This key value is generated from the supplied path name and proj value using an implementation defined algorithm. So proj is a integer. Path name is char star. Only the least significant bits of proj are employed by the algorithm, the least significant 8 bits. The application must ensure that the path name refers to an existing file to which stack can be applied. If different path names referring to the same file are supplied, ftalk will, with the same project file, the same key must be returned. Okay, so it's inode based, not path name based. Probably easier just to do it path name. To put things another way, ftalk uses the inode number rather than the name of the file to generate the key value. That might also mean that if you have multiple file systems where files have the same inode number but are on different devices, then you might run into the same issue. Because ftalk algorithm depends on the inode number, the file should not be removed and recreated during the life of the application. since it's likely that the file will be recreated with a different inode number. The purpose of the project value is simply to allow us to generate multiple keys from the same file, which is useful when an application needs to create multiple IPC objects from the same type. Historically, the proj argument was of type char, and it often specified as such in calls into ftalk. Susv3 leaves the behavior of ftalk unspecified if proj is 0. Under AIX 5.1, ftalk returns -1 if proj is specified as 0. On Linux, this value has no special meaning. Nevertheless, portable applications should avoid specifying proj as 0. This still leaves the choice of 255 other values. Normally, the path name given to ftalk refers to one of the files or directories that forms part of or is created by the application, and cooperating processes pass the same path name to ftalk. On Linux, the key returned by ftalk is a 32-bit value created by taking at least the least significant 8 bits of the project argument, the least significant 8 bits of the device number. Okay, so the device number is incorporated. And the least significant 16 bits of the inode number of the file referred to by path name. The last two pieces of information are attained by calling stat on path name. The glibc ftalk algorithm is similar to that employed on other Unix implementations and suffers a similar limitation. There is a very small possibility that two different files could yield the same key value. This occurs because there is a chance the least significant bits of the inode number could be the same for two files on different file systems, coupled with the possibility that two different disk devices on a system with multiple disk controllers could have the same minor device number. However, in practice, the possibility of colliding key values for different applications is small enough that the use of ftalk for key generation is a viable technique. A typical usage of ftalk is as follows. We say, hey, I want a key and an ID. Call ftalk on my file. I give it the character X, because why not? It gives me back my key. I could then use message get on the key to create or open up basically that message queue and get back the identifier. Associated data structure and object permissions. The kernel maintains an associated data structure for each instance of a systemv IPC object. The form of this data structure varies according to the IPC mechanism message queue semaphore shared memory and is defined in the corresponding header file for the IPC mechanism. We discuss mechanism specific details for each of these data structures in the following chapters. The associated data structure for an IPC object is initialized when the object is created via the appropriate get system call. Once the object has been created, a program can obtain a copy of this data structure using the appropriate CTL system call by specifying the operation of IPC stat. Conversely, some parts of the data structure can be modified using the IPC set operation, as well as data specific to the type of IPC object. The associated data structure for all the three IPC mechanisms, including a substructure IPC perm that holds information used to determine permission granted on the object. So they basically all have this IPC perm thing set on them. So I'm just making sure the stream is healthy here. Let me hit done on this because I forgot to do that. Boop. It says unstable. Refresh here. Unstable. Average stream bitrate too high. Okay. Does that mean I need to lower my bitrate? Let's see. YouTube is happy. Twitch is not happy. It says unstable. Let me hit up settings here. And then stream output bitrate Can I go to like 5,000 maybe? Apply. Let's ask AI. I don't like that it says unstable. I don't know what that means. Twitch, what is a good output video and audio bitrate? We'll say let's see. I'm streaming 1080p with 6,000 kbps, but Twitch says it is unstable, too high. Five. Let's set it to that, yeah. Excuse me. 5.5 and 160. That's what I have already. All right, let's see if it continues to complain. Oh no, it says excellent now. Okay, great. Thank you, AI. See, stuff like that, like AI, I love it. It just gives you the answer. It's like a better Google. Yeah, I mean, I would have not known what to do in that situation otherwise. If I look at my settings for YouTube, it doesn't mention bitrate or anything, so I'm assuming it's using the same settings. Cool. All right, so this is the IPC perm struct. What do we got here? So not going to look at the comments. I'm just going to look at the fields. So you got some hidden fields, these double underscore things. This key is most likely the key that identifies the IPC object. UID, GID, these are ownership, and they just use the system's UID and GID. CUID and CGID. That's weird that there's a creator and an owner. That is an unusual concept. Sorry, I looked at the comment here. So creator, I didn't know what these were. Yeah, like in Unix file systems, you don't have the concept of creator and owner that are separate. You just create a file and it's owned by you or not. Mode is of course a permission bits. Unsigned short is 32 bits, I think, on 64-bit architecture. And see how many bits is an unsigned short on 32-bit and 64-bit arch. I think it's 32 bits. 16 bits on both. Okay, so it's 16 bits. So 16 bits. So we have read, write, execute on owner, group, user group, and everyone. So that's 9. So it's enough to fit those. Oh, interesting. So if we have 3 times 4 plus 4 is 16. So that's why we have that many bits for our normal mode in Unix files, is We have 4 bits for the file type. Then we have 9 bits, which is traditional permission bits, read, write, execute for user, group, and everyone. And then we have another 3 bits for set UID, set GID, and the sticky bit. And when you add all those up, they are a short. They're 16 bits. So that explains why we have exactly that many bits and no more, no less. Okay, and then sequence number. Don't know what that thing is for. Cool. SUSE3 mandates all of the IPC. Well, let me highlight this. I want to do a video on that because I just realized that, and I think it'd be cool for people to know and understand what bits are available. SUSE3 mandates all of the IPC perm fields shown here except for key and sequence. However, most Unix implementations provide some version of these fields. The UID GID fields specify the ownership of the IPC object. The C UID and C GID fields hold the user and group IDs of the processes that created the object. Initially, the corresponding user and creator fields have the same values, which are taken from the effective IDs of the calling processes. The creator IDs are immutable, but the owner IDs can change via the IPC set operation. The following code demonstrates how to change the UID field for a shared memory segment. The associated data structure is of type SHMIDS DS. Okay, so we have our struct SHMIDSDS, so it's a shared memory ID. And then we use the SHM shared memory CTL. We say I want to stat this and read it into shared memory ID with this ID. So writes it into here. And then we can change the owner to some new UID. And then we say set, and we pass it in the same way. The mode field of the IPC perm substructure holds the permission mask for the IPC object. These permissions are initialized using the lower 9 bits of the flag specified. In the get system call used to create the object, but can change subsequently using the IPC set operation. As with files, permissions are broken into 3 categories: owner, also known as user, group, and other. And it is possible to specify different permissions for each category. There are, however, some notable differences from the scheme used for files. Only read and write permissions are meaningful for IPC objects. For semaphores, write permission is commonly referred to as alter permission. Execute permission is meaningless and is ignored when performing most access checks. Permission checks are made according to a process's effective user ID, effective group ID, and supplementary group IDs. This contrasts with file system permission checks on Linux, which are performed using the process's file system IDs, as described in section 9.5. Oh, so they completely bypass the file system IDs. Interesting. I mean, it makes sense because system IPC was not developed as like a Linux thing, and the file system IDs are a Linux thing. All right, we got this section. Okay. Let's continue onward. The precise rules governing the permissions a process is granted on an IPC object are as follows. If the process is privileged, cap IPC owner, then all permissions are granted on the IPC object. If the effective user ID of the process matches either the owner or the creator user ID of the IPC object, then the process is granted permissions defined for the owner user of the object. If the effective group ID or any of the supplementary group IDs of the process match either the owner group ID or the creator group ID of the IPC object, then the process is granted the group permissions defined for the object. Otherwise, the process is granted the permissions defined for other. In the kernel code, the above tests are constructed so that the test to see whether a process is privileged is performed only if the process is not granted the permission it needs via one of the other tests. This is done to avoid unnecessary setting the ASU process accounting flag, which indicates that the process made use of superuser privileges. Note that neither the use of the IPC private key value nor the presence of IPC exec_l flag has any bearing on which process may access an IPC object. Such access is determined solely by the ownership and permissions of the object. What is IPC exec_l again? IPC Excel. Creation failed if the IPC already exists. Exclusive. Okay. Some of these short names I just get confused sometimes, but that's the exclusive. It means that I am the owner and it shouldn't exist already. How read and write permissions are interpreted for an object and whether they are required depends on the type of object and on the operation being performed. When a get call is performed to obtain the identifier of an existing IPC object, an initial permissions check is made to it. It's kind of like the open in the rest of the system calls. Initial permission check is made to ascertain whether the permissions specified in the flags argument are compatible with those on the existing object. If not, then the get call fails with the error EAccess, except otherwise noted. This error code is also returned when permissions are denied. In each of the cases listed below, to illustrate, consider the example of two different users in the same group, with one user creating a message queue using the following call. So he said, IPC create, give it, the user has read and write, and the group just has read. An attempt by the second user to obtain an identifier for this message queue using the following call would fail since the user is not permitted to write access to the message queue. Second user could bypass this check by specifying 0 for the second argument of the message queue. So he's saying I want to read and write, but I don't have permission to write. In which case an error would occur only when the program attempting to an operation. See, this is what I don't like. This API mixes the concept of permissions with access that you're requesting. Like the open system call has a separate set of bits. Like if we just go man to open. So you have these flags and then you have the mode. The mode is only used if you are creating the file using ocreate with the flags here. Otherwise, this mode is completely ignored and the mode of the actual file is used. So they've segmented off the permission bits here and haven't put them in flags, and then flags then has a series of like I want read write, I want just read only, that sort of thing. If we look down here, so ocreate, if you specify that, then we do the permission bits thing. But if we don't create it, then I think there's like a read. Oh, read only. There it is. Yeah, here it is. O read only, O write, and those things go into the flags, not into the mode. So the open system call has this concept of the permission bits that you use to create the file along with the UMask, and then the permissions that you're requesting on the object. There's two separate fields in the system call, two separate arguments. Whereas with message get, man to message get, there's only one flag field here, and they cram everything and they repurpose things, which is like, I don't like that. So like read, they don't even have it because they're just repurposing the permission bits here. S, what is S? Seek. Stat. That's what it is. Stat. Sorry. It is for the stat system call. Okay. The second user could bypass this check by specifying 0 for the second argument, in which case the error would occur only when the program attempted an operation when requiring write permission on the IPC object. The get call represents the one case where execute permission is not ignored, even though it has no meaning for IPC objects. If execute permission is requested in a get call for an existing object, then a check is made to see if that permission is granted. The permissions required for other common operations are as follows. To retrieve information from the object, to read a message from a message queue, obtain a value from a semaphore, or attach a shared memory segment for read access requires read permission. To update information within the object, e.g. to write message to a message queue, change the value of a semaphore, or attach a shared memory segment for write access requires write permission. To obtain a copy of the associated data structure for an IPC object, the IPC stat CTL operation requires read permission. To remove an IPC object, IPC RMID CTL operation, or change its associated data structure, the IPC set CTL operation, requires neither read nor write permission. Rather, the calling process must either be privileged or have an effective user ID matching either the owner or the creator user IDs of the object. Otherwise, it errors out. It is possible to set permissions on the IPC object so that the owner or creator can no longer use IPC stat to obtain the associated data structure containing the object permissions, although IPC set can still be used to change them. Various other mechanisms specific operation require read and write permission, or the cap IPC owner capability. We note the required permissions in the following chapters as operations are described. IPC identifiers in client-server applications. In client-server applications, the server typically creates the system via IPC objects, while the client simply accesses them. In other words, the server performs an IPC get call, specifying the flag IPC create, while the client omits this flag in its get call. Suppose a client engages in an extended dialogue with the server, with multiple IPC operations being performed by each process, multiple messages exchanged, a sequence number of semaphore operations, or multiple updates to shared memory. What happens if the server process crashes or is deliberately halted and then restarted? At this point, it would make no sense to blindly reuse the existing IPC object created by the previous server process, since the new server process has no knowledge of the historical information associated with the current state of the IPC object. For example, there may be a secondary request within a message queue that was sent by a client in response to an early message from an old server process. In such a scenario, the only option for the server may be to abandon all existing clients, delete the IPC objects created by the previous server process, and create new instances of the IPC objects. A newly started server handles the possibility that a previous instance of the server terminated prematurely by first trying to create an IPC object by specifying both the IPC create and the exclusive flags within the get call. If the get call fails because an object with a specific key already exists, then the server assumes the object was created by an old server process. It therefore uses the IPC RMIDCTL operation to delete the object, and once more performs a get call to create the object. This may be combined with other steps to ensure that another server process is not currently running, such as those described in section 55.6 for a message queue. What is 55.6? What is 55.6? Just curious. 55.6 is running just one instance of a program, okay. Cleanup of IPC objects within a server. So we have this key file, should be an existing file or one that the program creates. So then we have our key, our message queue ID, and some permissions here where we request read and write for the user and just write for the group. Generate the key for the message queue, so we use ftalk in this case to generate the key, and then we do a while loop on our get with create and exclusive and the permissions. If it exists, then we do a get on the key with no permissions so that we can then use this RMID to delete it. Once it's deleted, then we continue looping until we get a -1, which indicates that there is no message queue, and then we can then create it again. Sorry, we create it in this call here. Sorry, I need to sneeze. Cool. All right, so the message queue gets created here. If it doesn't get created because it doesn't have exclusive access, then it returns -1, in which case we delete it and we try again. That's all it does. All right. Even if a restarted server recreates the IPC objects, there still would be a potential problem if supplying the same key to the get call always generates the same identifier. Whenever a new IPC object was created, consider the solution it just outlined from the point of view of the client. If the IPC object recreated by the server uses the same identifiers, then the client would have no way of becoming aware that the server had been restarted and that the IPC objects don't contain the expected historical information. To solve this problem, the kernel employs an algorithm described in the next section that normally ensures that when a new IPC object is created, the object's identifiers will be different even when the same key is supplied. Consequently, any clients of the old server process that attempt to use the old identifier will receive an error from the relevant IPC system calls. Solutions, such as that shown in listing 45.1, don't completely solve the problem of identifying a server restart when using systemv shared memory. Since the shared memory object is deleted only when all processes have detached it from their virtual address space. However, shared memory objects are typically used in conjunction with systemv semaphores, which are immediately deleted in response to an IPC RMID operation. This means that a client process will become aware of a server restart when it tries to access the deleted semaphore object. I guess the semaphore is like a read. What would they use a semaphore for? I'm curious. We'll see. Algorithms employed by systemv IPC get calls. Figure 45.1 shows some of the structures used internally by the kernel to represent information about systemv IPC objects, in this case semaphores, but the details are similar for other IPC mechanisms, including the fields used to calculate IPC keys for each IPC mechanism, shared memory, message queue, or semaphore. kernel maintains a associated IPC IDs structure that records various global information about all instances of that IPC mechanism. This information includes a dynamically sized array of pointers entries to the associated data structure for each object instance. Semaphore ID structure, in this case of semaphores. The current size of the entries array is recorded in the size field, with the max ID field holding the index of the highest currently in use element. Boom, 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 boom. So we got our IPC ID structure as 128 and use is 2, max ID. So size is like a capacity, in use is like length, max ID, I don't know what that is. Sequence, I don't know what that is. Oh, it's because you can null things out in between. Okay, I got you. Okay. Kernel data structure used to represent system v IPC semaphore objects. I guess the sequence, is that the actual value of that semaphore? Maybe. The list of when an IPC get call is made, the algorithm used on Linux, other systems use similar algorithms, is approximately as follows. The list of associated data structures pointed to by elements of the entries array is searched for one whose key field, so it's a linear search, O of n, matches that specified of the get call. If no match is found, the IPC create was not specified, then the error no ent is returned. If a match is found, but both IPC create and IPC exclusive were specified, then the error exists is returned. Otherwise, if a match is found, then the following skip a step. The following step is skipped. So this is if no match is found. So if no match was found and IPC create was specified, then a new mechanism specific associated data structure is allocated and initialized. This also involves updating various fields in the IPC ID structure. It may involve resizing the entries array. A pointer to the new structure is placed in the first free element of entries. 2 sub-steps are included as part of the initialization. The key value supplied to the get call is copied into the perm key field of the newly allocated structure. The current value of the sequence field of the IPC ID structure is copied into the sequence field of the associated data structure, and the sequence field is incremented by 1. The identifier for the IPC object is calculated using the following formula, which is the index into the entries array plus the sequence times the sequence multiplier. Okay, and the formula used to calculate the IPC identifier index is index of the object instance within the entries array, and sequence multiplier is a constant defined within the value so-and-so. For example, in figure 45.1, the identifier generated for the semaphore with the key value so-and-so would be so-and-so. Note the following points about the algorithm employed by the get calls. Even if the new IPC object is created with the same key, it will almost certainly have a different identifier, since the identifier is calculated based on the sequence value saved in the associated data structure, and this value is incremented by 1 during the creation of each object of this type. The algorithm employed within the kernel wraps the sequence value back to 0 when it reaches the value so-and-so. Thus, the new IPC object could have the same identifier as the previous object if 65,535 objects were created in the interim, and the new object reuses the same element in the entries array as the previous object. This element must also have been freed in the interim. However, the chances of occurring are extremely small. The algorithm generates a distinct set of identifier values for each index of the entries array. Since the constant IPC M&I defines an upper limit on the number of system V objects for each type, the algorithm guarantees that each existing IPC object has a unique identifier. Given an identifier value, the corresponding index into the entries array can be quickly calculated using the equation identifier but mod with sequence multiplier. Being able to rapidly perform this calculation is necessary for the efficient operation of those IPC system calls that were supplied with the identifier of the IPC object, i.e. those calls in table 45.1, other than the get calls. In passing, it's worth noting that two different errors can result if a process makes an IPC system call that specifies an identifier that doesn't correspond to an existing object. If the corresponding index of entries is empty, the error E invalid results. If the index points to an associated data structure but the sequence number stored in the structure doesn't yield the same identifier, then it is assumed to be an old object pointed to by this array has been deleted and the index was reused. This scenario is diagnosed with the error EIDRM. Sorry, I was on the wrong page there. All right, IPCs and IPCRM commands. IPCS and IPCRM commands are IPC analogs of LS and RM file commands. Oh, these are just command-like commands. Cool. IPCs. So you could see I got some message queues here. And then IPCRM. And I give it 2. Help. So IPCRM, a message 2. And then if I list it again now, I should have 478. Yeah. Cool. So I have no shared memory segments and no semaphores and some message queues that didn't get cleaned up for whatever reason. Can I clean this thing up? Vim sysv measure. So here I took away that I thought this would remove it. Maybe it just didn't get removed because it didn't get ran because I Control-C'd it. All right. Let's go ahead and remove these then. 4, 7, and 8. 4, 7, and 8. IPCS. And now if I run my build measure sysv IPC message queues, and I say, hey, if I do like 10 here, nothing. If I do like 1,000 and I do like 1,000,000 here, why is, oh, I'm hitting the wrong thing. There we go. If I do, oops, and then I hit Control-C, then it leaves this hanging around. I have to go in and manually remove it. IPCRM message queue 25. MSG. There we go. IPCs. Cool. On Linux, IPCs originally used the IPC stat CTL operation so that it could display information only about IPC objects for which we have read permissions, regardless of whether we own the objects. More recent version of IPCs use the proc sys v IPC interfaces and can display all objects regardless of permissions. By default, for each object, IPCs display the key, the identifier, the owner, and the permissions, expressed as an octal number, followed by information specific to the object. For shared memory, IPCs display the size of the shared memory region, the number of processes that currently have the shared memory region attached to the virtual address space, and status flags. Status flags indicate whether the region has been locked into RAM to prevent swapping, and whether the region has been marked to be destroyed when all processes have detached it. For semaphores, IPCs display the size of the semaphore set. For message queues, IPCs display the total number of bytes of data and the number of messages in the queue. The IPC's manual page documents various options for displaying other information about IPC objects. The IPC-RM command deletes an IPC object. The general form of the command is one of the following: IPC-RM-capx or lowercase x, key, and ID. I did not use the X. I used the message type. If I do IPC-RM help, it's said to use this format. But you can say X or capx, I guess. I don't see X flags here. If I do man on IPC-RM, yeah, it says the same thing. I don't see a -X or -capx, so this document's wrong, or out of date, I should say. In the above, we specify key as an IPC object key or ID as an IPC object identifier, and the letter X is replaced by underscore, by uppercase or lowercase q. For message queues, this is how you specify Q, S, or M. Thus, we use the following command to delete the semaphore identifier so-and-so. So they were saying to use this form instead of this form. Okay. So this is not wrong. I was wrong. I think it was. Obtaining a list of all IPC objects. Linux provides two non-standard methods of obtaining a list of all IPC objects on the system. Files within the proc sysv IPC directory that list all IPC objects, and the use of Linux specific CTL calls. So I'm just going to actually create another one here by running my program and killing it a couple times. So I should have 3 message queues, and if I ls under proc, it was a sysv IPC, and if I go under message, looks like it's not a directory, so I can cat this thing out. Gives me that semaphores and shared memory. So you can just access it via those files. We describe the files in sysv IPC directory here and defer discussion to the CTL calls until section 46.6. We provide an example program that lists all system v message queues on the system. Some other Unix implementations have their own non-standard methods of obtaining a list of all IPC identifiers. For example, Solaris provides the MSG IDs, SEM IDs, and shared memory IDs. System call for this purpose. 3 readme files in the proc sysv IPC directory include the same information as can be obtained via IPCs. Proc. Yep. Okay. Unlike the IPC's command, these files always show all objects of the corresponding type, regardless of whether read permission is available on all objects or on the objects. Example of the contents of a semaphore file is the following, with some white space removed to fit on the page. Great. The 3 proxys IPC files provide a non-portable method for programs and scripts to walk through a list of all the existing IPC objects of a given type. The best that we can achieve by way of a portable approach to obtaining a list of all IPC objects of a given type is to parse the output of IPCs. IPC limits. Since System V IPC objects consume system resources, the kernel places various limits on each of the class of IPC object in order to prevent resources from being exhausted. The methods for placing limits on System V IPC objects are not specified by Costudying 3, but most Unix implementations, including Linux, follow a similar framework for the types of limits that may be placed. As we cover each System V IPC mechanism in the following chapters, we discuss the associated limits and note differences from other Unix implementations. Although the types of limits that can be placed on each class of IPC object are generally similar across various Unix implementations, the methods of viewing and changing these limits are not. The methods described in the following chapters are Linux specific. They generally involve the use of the procsys kernel directory. Things are done differently on other implementations. On Linux, the IPCs-L command can be used to list the limits on each of the IPC mechanisms. Programs that employ the Linux-specific IPC info CTL operation to retrieve the same information. So I say IPCS-L. It gives me all the limits. Yeah, this is where you can see the message queue size. Okay. I never played with the size of the queue. That might have helped performance on my bandwidth tests. I just roll with the default. Alright, summary. System V IPC is the name given to 3 IPC mechanisms that first appeared widely on System V and have subsequently been ported to most Unix implementations and incorporated into various standards. The 3 IPC mechanisms are message queues, which allow processes to exchange messages, semaphores, which allow processes to synchronize access to shared resources, and shared memory, which allows 2 or more processes to share the same pages of memory. The 3 IPC mechanisms may have many similarities in their APIs and semantics. For each IPC mechanism, a GET system call creates or opens an object. Given an integer key, the GET call returns an integer identifier used to refer to the object in subsequent system calls. Each IPC mechanism also has a corresponding CTL call that is used to delete an object and to retrieve and modify various attributes, e.g. ownership and permissions, in an object-associated data structure. The algorithm used to generate identifiers for new IPC objects is designed to minimize the possibility of the same identifier being immediately reused if an object is deleted, even if the same key is used to create a new object. This enables client-server applications to function correctly. A restarted server process is able to detect and remove IPC objects created by its predecessor, and this action invalidates the identifiers held by any clients of the previous server process. The IPC's command lists the System V IPC objects that currently exist on the system. The IPCRM command is used to remove System V IPC objects on Linux. Files in the procsys V IPC directory can be used to obtain information about all the System V IPC objects on the system. Each IPC mechanism has an associated set of limits that can be used to avoid exhaustion of system resources by preventing the creation of an arbitrary number of IPC objects. Various files under the procsys kernel directory can be used to view and modify these limits. Further information, so-and-so. Goodhart and Cox. Is that? Let's see. Goodhart and Cox. 1994. Nope. Let's look it up in the back of the book. Is this the... Yeah, it's index. Let's see. There has to be like a... references, right? Here it is. Goodhart and Cox, the Magic Garden explained the internals of... It is this. James Cox. Going. there's this Russ Cox. I wonder if he's related to James Cox. Is Russ Cox Plan 9 / Golang related to James Cox? So this is published in what, 90 something? Okay. Yeah, I was just curious. Okay. Write a program to verify that the algorithm employed by ftalk uses the file's inode number, minor device number, and project values described in section 45.2. It is sufficient to print all these values as well as the return value of ftalk in hexadecimal to inspect the results in new values. Implement ftalk, verify by experiment. The statement is made in section 45.5 about the algorithm used to generate systemd IPC identifiers. I don't really care about doing any of that. All right, systemd message queues. Let's go ahead and write down our stopping point here, which was what? We are on page 937. And we're at time 11:32. So that is not great timing there. We spent about an hour and a half on what, 16 pages? That should have only taken an hour. This next section on systemd message queues, which is up here. System queues are the most familiar. I'm most familiar with message queues because I wrote the benchmark, but for the most part, I don't really have much experience with any of these APIs. So this will be what, 37 to 63. That's about 30 pages, about twice the length of this. Okay. Since it's 11:30, I'm going to have a break for lunch. I'm going to take an hour-long break and then 30 minutes for cardio. So I will be back at 1 p.m. to resume reading systemd message queues and semaphores and hopefully shared memory. We'll see how far I get on all this. But yeah, I will be back soon. Let me ban the spammer here. Get out of here. All right, cool. I'll be back in an hour and a half.